In cell segmentation, we're going to use the intensity of an image to segment out cells. We'll then use FIJI to quantify different aspects of each of the individual cells and the cells as a whole in the image. Activity 7 is the first step in cell segmentation, where we create two masks to use later on in the analysis. The cell segmentation activity can get very complicated. There are lots of different steps, so I advise that you follow this sheet as best as you can. I'm going to take you through the steps just now. So we want to be in the segmentation folder, and we're going to open up cell.tif. Okay, so the first thing we want to do is to duplicate this image. So I'm just right-clicking, hitting duplicate. That name is fine, so we can click OK. Let's just tile these. Okay, so in the first one, first thing we're going to do is to find the peak of each of these cells. So the nice thing about this stain is it's very strong in the nuclei, so it allows us to identify, hopefully, 1 point per nucleus. So to do that, we're going to process find maxima. And here we've got a prominence value, which basically equates to something like intensity. If we hit preview point selection, it would show you what it's found so far. You can play around with the numbers here, but the magic number that you want is something like 400. So in this case, you should find that most nuclei have only 1 point sitting within them. Now the key thing about setting up this type of automated analysis is you will not get it 100% correct. So for example, over here there's a couple of nuclei and there's only 1 point. Over here there's no nuclei. If you can get it as close to 100% as possible, then that's probably about as well as you can do. Okay, in this case we don't want to output the point selection. What we're going to do is something called segmented particles. So in this case it's going to try and draw a line in the gap in between each of these cells. Okay, so we click OK, and it provides us with something like this. We are going to save that as mask1.tif. So file, save as tif, mask1.tif. Okay, on our second copy of it, what we're looking to do is to identify the regions where the cell bodies sit. So we don't want to highlight the background, we want to just show where the cells are actually sitting in the image. So to do that, we're going to use an inclusive threshold. So image, adjust, threshold. Again, you can use the over and under for this if you want. The magic number I've got written in the instructions is 388, which looks something like this. Again, we're highlighting where the cells are, not trying to highlight the background. Okay, down at this point hit apply. There's a lot of rough edges and extra little bits going on here that's going to complicate the analysis. So we're going to clean that up a bit by using a process smooth or Control-Shift-S. You can see that's got rid of some of that finer detail. And now at this point we can hit apply. So what we've got, just let me save that. That's mask 2. So in this case we've got mask 1, which is showing the gaps in between the cells, and mask 2, which is showing the kind of footprint of the cells, where they sit within the image. Next thing we want to do is try and combine those two functions together. In the second part of cell segmentation activity 7, we'll combine the masks we've created and use those to read out quantitative data on an image. So to combine these two masks together, we're going to use one of the mathematical functions that sits under Process, Image Calculator. And what we're going to do is a mask 1 and, not add, A-N-D, and mask 2. So we want to highlight where the cells are and also the gaps in between the cells. So this will again separate out the cells, but here we're showing just the footprint of the cells. Now if we click OK, we're getting this, which is looking a little bit more like a segmentation of our original data. Now again we're going to clean it up. We've got a few little pieces in here and we can use the Analyze Particles tool to filter that out. So in this case, let's filter from anything smaller than 250 pixels squared to infinity. We're going to exclude on edges. We don't want to show any results at this point. We're just filtering it out, and then we're going to create a new mask after this. If we click OK, we can see we've now got rid of anything that's touching the edges. So for our area readouts, we should be fine. But there's something a bit weird happened to the look of this, so now our lookup table has been inverted, and this happens when you use the Analyze Particles. All we need to do is go into the lookup table menu and hit Invert Lookup Table. Okay, so that looks better. Background is black. What we're selecting is white. The other thing we've got is a couple of cells in here have got little holes in them, so we want to fill those in. So we want to measure the hole of the cell. And we're going to go to Process, Binary, Fill Holes. To do that, hopefully you'll see those holes have disappeared. So this is finally our final mask saying these are our cells, these are the regions that we want to analyze. Let's save this as mask 3. And then finally we can go on and actually analyze the data. So I'm going to get rid of all of the previous steps. So we just have mask 3 and that cell.tif image open. And what we're going to do is use the mask to say this is where we would normally, this is where we want to analyze, but we actually want to read out the data from this image. Now normally you wouldn't quantify the same image you've used to segment. That's not a good way of doing things, but we're going to use this in this case. Okay, so how do we do that? How do we use the mask to actually analyze on a real image? So we're going to go to Analyze, Set Measurements, and set the readouts that we want. So in this case we're wanting area, shape descriptors, integrated density, mean gray value. Let's go with perimeter, ferrets diameter, and display label. We don't want limit to threshold, but we want to redirect it back to the cell.tif image. So we're saying use this binary mask, but redirect the measurements back to cell.tif. So hit OK. Make sure we've still got our mask selected. We can then go back to Analyze Particles. Again, we can use the 250 to infinity. In this case, we want to show outlines. And we want to display results, clear any old results, and also summarize. We've got exclude on edges selected there, but that's already been cleaned out. You could also use Add to Region of Interest Manager if you wanted to go in and manually clean out some of the data as well. In this case, we'll hit OK. And now we've got our outlines showing all of the cells that have been identified. Our summary showing that there's 368 cells, and these are the total or average statistics. And then also you have those measurements for each of those 368 cells. And again, we can save both the tables as a CSV file and the outlines as a TIFF file. Activity 8, Advanced Segmentation. In this, we use image calculator and binary options a little bit further to create new masks for analysis. Next, we want to take it one step further. So we're going to look at creating cytoplasmic masks and also paranuclear masks. So for the cytoplasmic mask, we need to open nuclei.tif within the segmentation folder. And again, we're going to go through a similar setup as we did before. So image, adjust threshold, make sure you're happy with that. Create a binary image. Let's go into process binary and run a watershed function just to separate out any that were joined. And then we're going to save that as mask n. And we're also going to open up mask 3. So if you hadn't saved that already, it is already sitting inside your demo data folder. And what we want to do is take away the nucleus area from within these cells. So again, we're going to use a bit of image calculator, so process, image calculator. And in this case, we want mask 3. And we're going to subtract mask n. Okay, so in this case, we're creating lots of different fried eggs there that again we could use, redirect back to whatever image we want to analyze, and in this case we're looking just at the cytoplasm, not at what's in the nucleus. You could also use the nuclear mask for looking at intensities just in the nucleus. So this is a very good way of doing your ratio between nuclear and cytoplasmic stains. While we have the mask n open, if this ever happens, just go back to threshold, reset. Okay, what we want to do here is create a paranuclear mask, so measure just the intensities on the edge of these objects. So in this case, I'm going to duplicate these images again. And we're going to rename them. So let's rename one dilate. And we're going to rename the other one erode. Ooh, type. And you'll never guess what we're going to do with these. Okay, so for dilate, we're going to go to process, binary, dilates. Now if we got our binary settings correct, that will have added one line of pixels around the outside of our object. And then the other, we're going to erode, so process, binary, erode. In this case, again, if our settings are right, it will remove one line of pixels around. And then in this case, we're going to again do a bit of mathematics. So image calculator, we want to take the dilate and subtract the erode. And that gives us lots of little donuts that we can use for analyzing around the outside of structures. In this case, the nucleus, but it could be the cell surface or something like that. Activity 9, Intensity over time. In this activity, we use region of interest tools to measure intensity in a time-lapse image. So to measure intensity in a time-lapse image, we are going to go to intensity over time and open up this calcium flux.tif image. Here, if we play the movie, you'll see we've got little bursts of intensity as this calcium indicator flashes with some pulses of calcium. So we want to look at those intensity increases over time. So in this case, we're going to use a region of interest tool, something like oval or rectangle. You can choose whatever you want. So we can just draw a region of interest, go to Analyze, Set Measurements, In this case, we just want something like mean gray value. Make sure we don't have limit to thresholds ticked. Click OK. And then if we go to image, stacks, plot z-axis profile, so in this case our z-axis is time. That will plot a little graph of those intensity peaks and also give us a little table here that we can save out as a CSV. So you could do this manually over a heap of different cells and positions within the image, or you could use the region of interest manager. So to use this, we're going to go to Analyze Tools, ROI Manager, and here we can add that in. We can add in some background regions, a couple of other cells. You can also go in and rename these as well, so you know exactly what they are. If you hit Show All, it will show all the regions of interest in your image. And then if we go to More, Multi-Measure, we want to measure all 50 slices, that's our time lapse, and we want 1 row per slice. And if we hit OK, that's going to give us our mean intensity for region of interest 1, 2, 3, 4, and 5. And again, this table can be saved as a CSV file. Activity 10 is Euclidean distance measurements. We can use this to measure the average distance between objects in our image. For the Euclidean distance measurements, we're going to open up the ECD folder and open nuclei.tif. First thing we're going to do is set a threshold to identify the nuclei, and then hit apply to create a binary image. We might as well add in a woodshed to separate out any structures that are touching. Next thing we want to do is to go into binary options, process binary options, and make sure our EDM output now is set to 16-bit. Okay, next thing we're going to need to do is to invert the image. So we're not inverting the lookup table at this point, but the image. So edit, invert. So in this case, our structures we're interested in have 0 intensity and the background has high intensity. And what we're going to do is go into process, binary, and distance map. Okay, so what this does is it looks at our 0 intensity, and for every pixel it goes away from that 0 intensity, it adds 1 intensity value. So in our Euclidean distance measurement here, the brighter regions are further away, or regions that are further away from objects, and the darker ones are closer to the objects. To help us visualize this a little bit better, we're going to use a lookup table, and in this case we're going to use the 16 colors lookup table, which is kind of cool. Next we want to set the measurements. So in this case we want mean gray value. We're going to set a threshold in a second, so we're going to limit to threshold, and we want display label. Okay, next thing we want to do is we want to identify, or we want to count the grayscale values in the area that isn't including our structures. So in this 16 colors, the black is our structures, and the blue, greens, yellows, and reds are the actual intensity from the distance measurement. So make sure we've got this window selected, image, adjust, threshold, and we want to bring that down So we're at 1, so we're not quantifying our structures, but we're looking at the intensity beyond those. So 1 to 65,000 grayscale values on a 16-bit scale. Again, we're not going to hit apply here because we're quantifying what's in the thresholds. We've got to analyze, measure. And this is giving us a mean intensity of 8.093 across the entire image. Now, even if your image is calibrated, this one isn't, this is in pixels, but even if your image is calibrated in microns, the intensity scales with pixels, so it's, if you remember, it's adding 1 intensity unit for every pixel. So this is actually a pixel value, even if your image is calibrated. So you'd have to go back, work out what your pixel dimensions are, and multiply the size of the pixel by your mean value here to give you an actual average distance between the objects. Activity 11 is macro recording. This is very useful if you're performing repetitive steps over and over on multiple images. So to record a macro in FIJI, we want to go to Plugins, Macros, Record. And this window will open up, and anything we do from this point on will be recorded up here. So first thing I'm going to do is open up, let's go with a batch macro. Let's open nuclei1.tiff. So we'll see select window nuclei1.tiff. And for this example, I'm going to count the nuclei within this image. You can obviously repeat whatever activity you want to in this case. So I'm going to image adjust thresholds. Does that look okay? That looks okay. Hit apply, process, binary, watershed in this case. Let's go to analyze particles. Let's clean this out a bit. So let's go something like 100 to infinity. Let's exclude on edges, create outlines, display results, clear results, and summarize. And hit OK. And that's our final data that we want to get out of our macro. Okay, so over here you can see lots of different steps that I've done. I haven't messed up, but if you mess up and start clicking wrong buttons and things, then this will all get recorded as well. So it's a good idea to look through it and try and make sure that it makes sense. So the first thing I'm going to get rid of is this, because we don't always want to be opening up. We might not always have a nuclei-1.tiff image. So here set our threshold, default dark. This doesn't actually do anything, but we can leave that in there. Convert to mask, run a watershed, and then run the analyze particles tool with these settings, and that should then give us that final result. If you feel like you're done, then you can hit create here, and that will create your macro that you can now test. If you're signed up for the FIJI macro writing for biologists workshop, Ellie will take you through what all the different colors and things here mean, so it'll help you in terms of how your macro looks and finding any problems that you might have. I'm just going to close all these windows, and we're going to try and run this macro that I've written on this nuclei1.tiff image. Okay, so if we hit run, hopefully we don't get any errors, and it basically duplicates what we've done before. Okay, once you're happy with this, you can go to File, Save As, and then give that macro whatever name you want, but it needs to have the IJM at the end there to be recognized an ImageJ macro. Okay, so let's call it nuclei.ijm. So let's close down all these windows. Okay, so now I've got my ImageJ macro there. I can drag and drop this again if I want to run it, or you can also go into plugins, macros, run, and then try and find that on the desktop and run it that way with an open image. Activity 12, Batch Macro Analysis. This allows you to automatically run your macro on a group of images within a folder. Okay, so to run a macro automatically on a number of images within a folder, we can use a batch macro analysis. In this case, we want to go to Process, Batch, Macro. And this allows us to define what our input folder is. So in this case, we're going to go to Quantification Workshop, FIJI Demo Data. Let's use the batch macro analysis. Click OK. I have a folder called Output sitting here. It's always a good idea to output into a different folder. You don't want to overwrite your initial data. You can get it to, if you have any generated images being generated, get it to output those as different file extensions. You can add a macro from a selected list. You can also say I only want an image, or I only want to analyze anything that says nuclei or anything that's a .tif file if you've got a folder with a mixture of different images within it. And in this case, let's copy and paste into here the macro that we've just written. And if we're happy that it's going to the right place and from the right place with the correct file extension, if we now hit process, it should go to each of those folders, to each of those images in turn. That's this one. So it doesn't like the .ijm file, it can't analyze the IJM file. So here we've got counts for each of the 7 images that are here. We've got our summary statistics, and we've also got our individual data stats as well there.